we are going to perform a Sieve analysis for particle size gradation of a granular soil. There are two important points. First, it is a gradation of a second granular soil. So a granular soil generally represents a sandy soil, or even if it is a C5 soil, the C is very less, phi is predominant. Now, why we need a gradation? You see, this is my index finger, and I use this index finger to point out its particular thing. This is how we use our index finger. Similarly, there is a set of parameters or properties of a particular soil which we call together as index properties of soil. Why we call them index properties of soil? Because based on those index properties, we can actually point it out what type of soil it is. That means those are indicative of the inherent nature of the soil sample. Now we are going to perform a Sieve analysis. A Sieve analysis is Sieve analysis will give us what are the grain size distribution or the grain size grading of that soil. Why it is important? It is important because based on the grading size, we will have an understanding of what the soil type is. That means if you are going to construct a building, you need to assemble your foundation beneath the soil. So it is very important to understand the soil parameters. So with this experiment, this Sieve analysis, we will have a first-hand understanding of what the soil type is. Of course, we will need some more sophisticated parameters and experiments which you will learn in subsequent classes to completely understand what the soil strengths are. But this is one of the first and very primary experiments that you are going to come across throughout your working life. So I ask you to kindly pay attention. This is very simple, but at the same time it is very quantitative. So what we have a set of sheaves, 1, 2, 3, 4, 5, 6 and 7 sheaves, and the sizes of the sheaves ranges differently. Now if you say the sizes of the sheaf, it means what is the porosity. That means what is the size of these pores or these meshes in this sheaf. For example, this particular sheaf is 4.75 mm. It means that the size of the mesh is here 4.75 mm. Similarly, if I take these two, the first one is 2.36 mm and the second one is 1.18 mm. What does it mean? It means the size of the mesh here in the first one is 3.26 mm, while the size of the mesh in the second one is 1.18 mm. What it will do, if it will let the different materials, different grain sizes pass through it, it will let the particle size which are less than 2.36 mm pass through it, and it will retain any particle size which is bigger than that. Similarly, for 1.18 mm sheaf, it will let pass 1.18 mm particle sizes through it, and it will retain anything which is bigger than that. So we will have 7 sheaves here: 4.25, 2.36, 1.18, 600 micron. Now this is a micron. This is 425 micron. This is 300 micron. This is 150 micron, and finally this is your 75 micron. So you see, I want to show this is a very fine sheaf. That means any particle whose size is bigger than 0.75 mm, it will retain here. Which size is bigger than 75 micron, and anything which is smaller than 75 micron, it will let it through. Now in this experiment, we need to put half kg, that is 500 mg of soil here with us. The procedure says that the soil should be oven dried for 24 hours we have already completed that process, and this is where we have taken 500 milligram, that is half kg, sorry, 500 gram, that is half kg of salt with us, and you can see there are different particles here. You can see how big it is, and from here you can see how fine these particle sizes are. That means it is an assorted matrix of different particle sizes of fine particle. Now here our very efficient Mr. Shankar is helping me out. So you see what he is doing here. He is just gently putting all the soil particles on the 475 mm sieve. This is 4.75 millimeter sieve, where all the particles are gently put. Now either we can do a mechanical sieving, where there is a mechanical instrument which will mechanically sieve it for around 10 minutes, but rather we'll go for a manual, or Shankar will do the sieving for us here, and you can see that the idea is to impart an irregular motion throughout the sieves. We are not doing any specific motion. What we are trying to do, we are trying to impart an irregular motion. Yes. At the same time, we also ensure that no particle is pushed through. Now you see, I took this 4.75 mm sieve, 4.75 mm sieve out, and these are the particles which are retained on this particular sieve. Similarly, these are the particles which are retained in this is 2.36 mm sieve, and this is retained there, and so on and so forth. So what we have here, yes, so like this you can see that we have retained everything. And you can see these two are very fine indeed, so there are not much of a, well, I can again try it that way, and yeah, there is not such difference. This has already been whisked properly. Anyway, we take the sample which is retained on each sieve at a time, and again we'll weight what is the portion. We'll weight the portion which is retained on each of these sieves. So again we are going to our weighing machine. We have to adjust it, and you see that 0.095 kg, which is 95 mg of the fraction of the particles are bigger than 4.75 mm. Now please note that we will note it down 0.095 kg with the units in kg, and we will use it for the further analysis. Now we take out the finest of them, 0.7 this is your 75 micron sieve, and we take out what is the retain on the sieve, and we again weight them. So I have shown here the calculations for two particular portions, and you see that is 0.13 kg, which is your 13 mg actually. This much of sieve, this much of granular material was retained by your 0.75 micron sheave, and similar procedure will be followed for all the sheaves. Here you can see that we will take out what is written on each sheaf, and we will again take the weight and of that particular sheaf portion, and we are going to calculate. Now once we calculate the weights of each portion which has been written in individual sheaves, we will put them in a tabulated format. Then we calculate what is the percentage in terms of weight. That means we will calculate the cumulative weight, and we will again divide it by, we know what is our initial weight, we know weight retained in each part. So this is simple, B by A or B by BI divided summation of divided by summation of BI equal to 1 to n. So with this simple formula, what we are going to do, we are going to plot, and I will show you here a very beautiful curve here. You can see that if we plot the percentage finer on y-axis and particle size on x-axis, we will get a curve, we will get a very beautiful curve like that. This is what we will call the gradation curve of this particular soil type. And based on this particular soil type, we will calculate what is D30, what is D60 and what is D10, and then we will again proceed with some other specific calculations. In those with those calculations, we can quantify what is the gradation of the soil, which we will discuss in a subsequent theory class. So you see, this curve is very uniform throughout. That means it represents a uniform distribution or uniform representation of different particle sizes in the matrix of the sample taken. This type of curve we call a uniformly graded curve. Similarly, we can have a polygraded curve, a fine graded curve, and this type of properties are very, very useful for geotechnical engineering. So with this, we will come to the conclusion. There are certain theory parts which are very, very important, and we will discuss it again in the next class. Thank you.